Welcome to another lecture, guys. It's so good to see you in the lecture. And I'm just saying hi for those who are watching recorded lectures. You guys are really missing out on the fun that we have, in between the lectures. Or let's say when we stop the recording. I'm just making you guys miss out on fun. But yeah, all right, I guess. It's glad that you have reached up until this chapter, and I hope things are going well for you. Okay, so now we are going to continue with what we tried to study in the last lecture. So what we studied was something about creating, so we kind of created a new theoretical model for us to analyze the information that we have at hand. So we know the first information that we have at hand is the number of people who have died, and basically not exactly the number of people who have died, but the lives that we're observing, we would know whether they have died or not up until when we pause the observation, up until when we define the observation to cease. So that's one thing. And the other thing that you would subsequently know because of this, because of the nature of the problem that we have defined, is the number of times, basically the waiting time, the time that each life will spend under your observation. So this too will in a way help you to derive, we are expecting that these two will help us derive the transition rate. And we have already seen the connection between the transition probability and the transition rate. So once we know the rate, we can also know the transition probability. So now we'll move forward in figuring out the transition rate using the information that we have at hand. So now what we have seen is the function for, so we have seen the joint distribution function, right, of D and V. So let me just write. What we have seen is joint probability distribution of, so remember when I'm writing random variables, I am going to use capital letters. And that is why I have capital D and capital V. And again, if I'm observing these for each particular i's, so I'll have e raised to minus u vi times mu raised to di. And what happens is if I'm looking at everyone, then I get this thing as uv and mu raised to small d. So this is how I certainly define my joint distribution that I have to concern myself with. So again, we will try to use now the MLE, which is the maximum likelihood estimator, to figure out the optimum value, the consistent estimator for this mu guy, which in a way denotes the transition rate here. So we hope that we will get something which makes much more intuitive sense. So let's just try to do that, I guess. It's fairly straightforward. So if I were to define the likelihood function, I know that my likelihood function will just be e raised to minus mu v and mu raised to small d. Let me just stop the notation. Yeah. So I have mu raised to d, right? And again, I know that I want to work with log L because it's easier. So what I will get here is minus mu v. And here I will get plus d log of u. Just give me a minute, guys. I think this. All right, I'm just hoping that the battery isn't dying. All right, so now once we have this log of L, what we want to do is we want to differentiate this log of L with respect to what? Anyone? What will I differentiate this log of L with respect to?
U.
U, right? Because that is the parameter in interest. So we'll differentiate this with respect to mu, and what do we get here? Minus V. And here I will get plus D upon mu. And now I will just equate this to 0. So what do I get here? I get that my mu hat. So remember, once I equate this thing to 0, this mu will become mu hat because this is an estimate of this mu, which comes from the sample that you have observed, not the population mu. So this sample mu is just going to be d upon v. What is this? This is just d upon v, right? So again, you can also, resort to checking whether this is indeed the maximum or not, which you can do. This pen is not behaving properly, but what you will have is minus d upon mu square, which is less than 0 for sure. So I guess that's just it. So now you always observe this d, you always observe this v. What is this v? This v is the total time spent under the observation by all of the lives combined. And what is this d? This d is the number of deaths you have observed out of the lives that you have observed. So again, this kind of makes sense, right? Because what is my mu? My mu is figuring out the rate at which people die if they're alive at one particular point in time. So again, what I've done here is the time that these people spent under observation is in the denominator, and in the numerator I have the number of people who have died when we were observing them. So I think it kind of makes intuitive sense as well when we are talking about this mu, particularly let's say as mortality rate, and that we will see in upcoming chapters. So again, this actually v, when I say v, is also, this v actually has much wider interpretation than just the waiting time or just the time spent under the observation. It is also the time when these lives were exposed to risk. So whenever I'm saying risk, this risk is the risk of being dead. So that's the risk that there is, and this is, at least from the observation point of view, this is the time when all of these people were exposed to die, were exposed to the risk of being dead. So sometimes this is also called being exposed to risk. And again, the risk would be dying in this case. It could be other things in other cases. So let's say if you're looking at the machinery failures of the machine, then it would be the risk that your machine will fail and it will not work, and so on and so forth. So this is just your MLE estimate of your mu. So I guess this is a pretty important result, and yeah, this is very nice because of the intuitive sense that makes. Okay, so now again we have this mu. So generally what we will do is so from the table that I did show you guys before, you will have d, you will have v, you can figure out your mu hat easily, right? But now we also need to be sure of, how sure are we of this mu hat? So sometimes, as we know, point estimates aren't the only thing that will be the best. So you might want to see whether you can get a confidence interval around this mu hat, so as to be much more precise with the estimates that you might put out. And again, there would just be a verification test sort of a thing that you can do. So now we will have a look at how do I figure out. So if I want to figure out the confidence interval for mu, I will have to figure out first its distribution, and which will, in a way, I think will help me to figure out its mean and its variance, right? Because that will help me to write my confidence interval at the end. So we'll now try to see and have a look at some of the properties of this maximum likelihood estimator. So what I'm going to do is, because this is not of much use for now at least, what I want to do is just take you guys through this thing. There are some results which will help you to do just that. So to figure out the distribution of your mu, and again, you won't necessarily have to, basically figure out or prove these distributions, but there are just some identities that will be very helpful, and there are just some results that will be very helpful. So for those who are interested in how things are derived, I'm just going to walk you through the derivation that they have given in the book. So they say that, there are some results that you observe. One is this and the other is this. So they are basically trying to prove how they arrive at this and how they arrive at this. So again, yeah, they have said, right, at least we need to know the expectation and variance of this mu. Okay, so they have written mu tilde here, right? And now when they're writing mu tilde, it means that my mu tilde is the random variable. So this is my random variable. And if you see, if you have a close look, the mu hat was in terms of small d and small b, because that was a sample estimate. And now this is an estimator. So that is why this is in terms of random variables. So mu tilde is just capital D upon capital V, which are again the respective random variables for small d and small v. So I guess that's clear. So now whenever you take expectation, you know you should never write small d in there. There should always be capital DI and capital VI. So that's one thing that you should always keep in mind. But again, we'll have to prove these sort of two results and we'll have a look at that. But again, even before we do that, what they're doing is we know the probability. Just give me a second. So yeah, so what we know is the probability function of DI/VI, which was the joint distribution function that we derived, right? So maybe we can go back and have a look at that distribution once again. So this was the distribution, right? This was basically the joint distribution of our DI and VI. But now again, if we have a look at all the possible values, so what we will get is something that they have written over there. So to even interpret this interval, this integral, what the first term says is, so you know what's happening here, the first term in the first, okay, so even before I actually explain, can anyone tell me what you understand of this integral and this sum being equal to 1? Do you guys understand this? Can any of you kind of try to guess from this what this and this represents?
No. Is it the TPX and QS?
Is it the TPX and
QS?
QX? Okay. Okay. Why do you think that's okay? Fine. But yeah, go on. Sorry.
Because the first integral is e raised to minus mu vi mu, which is just a second. Oh no, it's not. Sorry.
Yeah, it's all right, I think. But you were thinking on the right track, I would say.
The first integral is the probability of life x living up to VI and dying instantaneously, right?
Exactly, yes. So we are kind of taking the two possible values of DI that we can observe into account. One is that it's 0, which is the first integral, where you are saying that this guy can basically die anytime in between 0 and DI minus AI. And the second term that you're adding is the possibility, the first term is the possibility where your DI is 1, right? Where the guy can die in between the observation period. And the second thing that you're adding is the time where this person actually does not die. So this is precisely the thing that I guess Sauri was trying to say, which will be Px plus AI. And here you will have Vi minus AI, which is why you get e raised to minus mu Vi minus AI. And because these are the only two possibilities, either a person will not die or a person will die. So this will always add up to 1. So now what we'll do is we will use this identity to kind of prove certain things. So let's see. Do you guys understand this integral and this expression here? Each one of you?
Yes, ma'am.
Yes, ma'am.
What about Vanshita?
Yes, ma'am. So I'm just guessing. Can I say that?
Yes. Go on.
Like it was like the 82nd birthday to 83rd birthday. So is it like the combination of the probabilities that a person will make it to 83 or will die between BI minus AI or something like that? I'm just guessing.
Okay, so it will be the fact that, so okay, let's say that we start observing that particular person at 82.25 years of his age, and we will observe him until he turns 83, right? And what we are saying here in this particular case is that he dies before he turns to 83. And we don't know when that could be. So we are assuming that VI is the basically the time he spends under observation, which will be, maximum it can take is something which is right below BI minus AI. So here we are taking into account the fact that he could die even before he reaches his 83rd birthday, which is sad. But here we are taking into account that he does not die, at least up until his 83rd birthday. We don't know what's going to happen next. We can only say what's happening from 82.25 till 83rd. Does this make sense?
Yeah, that's what I meant. So it was right? Like what I thought was right.
Yeah. If this is what you meant, then yeah, you're correct. Yeah. So I guess yeah, you said it correctly. So yeah, this is what this is about. Very good, great going, Vanshita. Okay, so now what we have here is this. They have just calculated this expectation. We don't want to do that. Okay, so now this is what they are saying is the probability that your life I will die between this and this exact age, which is what we just saw here, right? This. So this e raised to minus mu vi is precisely this part, and this is precisely the part that you get if you assume your mu is constant. So this is just version with less assumptions. Okay, so that you have, yeah, which they have precisely written here. So now if you want to figure out the expectation of di, you know what is my expectation of di? It is just equal to the probability that my di will be equal to 1, which is q of x plus ai and bi minus ai here. And I know that the probability that my di will be equal to 1 is nothing but precisely this interval, right? It's 1 meaning that this person can actually die anytime. So the very first integrand that you have is precisely the same that you have here. So once you have that, what they have now done is they have just rewritten the f of vi, which we tried to write in the case of, when we solved that particular sum. So here we don't have 0.75 and less than 0.75, but rather general terms bi minus ai. And this is the point mass probability, and this is the density that you will have. So this is again trying to figure out the probability that you observe a life, which is alive, up until x plus ai plus vi, and then this person dies instantaneously. And that is why the observation is less than the actual observation period that you would have thought of in case the person did not die. So here, if the person does not die, you observe him for the full observation period. And here you cannot see anything about this person being dead because when you started, he was alive. When you ended, he was still alive. So all you can say is that this person was alive when I started, and this person is still alive when I ended, basically. So the addition will give you bi x plus bi here. So I guess that was it. And they have just rewritten this thing again in terms of u and vi's and everything, that stuff. So now what they have again derived this expectation of vi in the similar manner we derived it in the previous question. So I guess this is kind of easier now. So I'm just gonna go through for anyone who is interested in the details can actually study this in details, but I'm just gonna tell you guys formally what's going to happen here. So we start from the result wherein we said that, this probability plus this probability is equal to 1. So what we will do now is we will differentiate on both the sides with respect to mu, which is the parameter of our interest here. So if you differentiate this guy, you see that there is some integral which takes values 0 and bi minus ai. So thankfully for us, these limits do not depend on mu. So our life is easier. What you will do is you will just differentiate these things, this integrand that's in here. So you will use the chain rule again, and you will have e raised to minus mu vi, differentiation of mu, which is 1 here. And here you will have mu as it is, and differentiation of this guy, which is minus vi e raised to minus mu vi. So you see minus vi e raised to minus mu vi and dvi as it is. And here if you differentiate with respect to mu, you get precisely this. And when you equate this to 0, and that is when you will solve again now through this thing. But again, you will see that you don't necessarily have to solve for everything, because now once you have this, so now once you have this equation here, you can easily separate this integral and this integral as two different integrals. So in one right hand side you will have this everything, and in the left hand side you have this thing. And if you observe, whatever you have on this right hand side is exactly what you get for the expectation of vi, which was something that we derived here. So if you check, this term is precisely the same, and u vi e raised to u vi, u vi e raised to u vi, right? Integration from 0 to bi minus ai, good for us, right? So now we can just easily write that this is nothing but expectation of di here. And now what's going to happen is here, if you multiply mu on both the sides, what you get is the expectation of di on the LHS. And that is how you prove that expectation of di is just equal to mu times expectation of vi. And this is what you will be using later on to figure out the distribution of mu I. I mean, to figure out some sort of a nice distribution for your mu. But again, now remember, whenever we use MLE, it does not guarantee us that the distribution of the parameter will be normal, but most of the times under some regularity conditions, and let's say if there are some boundary conditions which are satisfied and there is some root and consistency that they expect of MLE estimators, if those sort of conditions are true, then you can easily see that, these will always follow a normal distribution. But again, we know the kind of things that will help us to determine its distribution is one, the law of large numbers, and second, the central limit theorem. So these are two favorite theorems which we are going to use now. So first of all, I know my expectation of this guy, right? Expectation of this guy is 0. And again, let me just maybe rewrite here. What was the variance? I don't remember. But yeah, so basically, I haven't showed you guys the proof of variance. It is actually in the problem solving part. So we can maybe do that later on. So let's just stick with knowing the derivation of variance. And you can trust me on the derivation of expectation and just trust me on the variance part. So I'm saying that my variance of di minus mu vi is equal to expectation of di. Okay, so this is my result. Let me erase this and I'm just gonna write for mu there. Okay, so yeah, this is what I have observed. Oh, it was right here in front of my eyes. Okay, so now that we know the expectation of this guy, the variance of this guy, let's just try to figure out the distribution of this guy if we can. So again, we will not be actually figuring out the distribution of d minus mu v. but we will use our d minus mu v to figure out the distribution of mu, which is what interests us. And I know that, we have already derived that my mu is just d upon v. So I guess now that we know that, what we are going to do now is, let's just say that this is 1 upon n d minus mu v. And again, I'm just taking average. So this is just going to be like average over all the values that I have observed. So di and vi is the pair that I observe for each and every individual that I consider as a life. And what I'm doing is I'm just taking di minus mu vi. This is just a new random variable that I have defined for now. And I'm summing it across for all of them, and I'm dividing it by the number of lives I observe. So this is like taking average. So again, now if I can assume safely that this average will always be less than infinity and the variance is also less than infinity, so I can see that this random variable here behaves like a normal distribution when n gets fairly large. So this assumption is due to central limit theorem. And then you can basically say that, 1 upon n d minus mu v follows normal with 0, because the mean of this guy will be 0, right? And the variance is what? Expectation of di. So because you have 1 upon n as well, this will go in as the square. So you will have variance of di minus mu vi upon n as 1 upon n square times expectation of di. So this is what you observe as the variance of this particular guy. But now we also know that I can rewrite my estimator of mu as d upon v. So what I'm going to do is I'm just going to subtract the actual population estimate of my mu from the estimator, and what I get here is just d minus d upon v minus mu. So I did this, why? Because this you get in the numerator, and this I know a lot more about than just d and than just v. So what I know is that now in my numerator I have d minus mu v upon v. And again, I can just divide and multiply n here, so that I'm precisely going to use this derivation now to think about this mu guy here. So now again, this is not rigorous, and again, you don't have to, remember how they are deriving this, but just so you guys know how to go about solving this. This is kind of technically, as they've said here. Okay, so maybe let's just, okay. Now what we are going to do is we are saying that my n, I'm taking it till infinity. So because I want to use my law of large numbers and central limit theorem, I know that I'm taking my n to infinity. So I expect that if this is equal to this, I expect that these limits will also be equal. But now what they are doing here is, we know something about this. We know a whole lot more about this d minus mu v upon n guy, right? So if I were to take expectation of this guy here, I can easily say that this is something like this. But what I would have here instead is v upon n. So what I'm going to do now is, they are saying that by using the law of large numbers, v upon n goes to expectation of vi. So what is my v? It is the total time observed for all the lives that are being observed, right? So it is v1 plus v2 plus v3 and so on till v capital N upon n. So assuming that, again here you will have to assume that vi's all have finite expectation, then only you can expect this particular sample average to pertain and to basically go in limit to the population expectation of this particular random variable vi here. And there is something known as convergence in probability, which you did not know, I would say, for now. So this was actually where I started, my econometrics during my master's. This was the very first thing that we learned in the very first class, convergence in probability. Then you have convergence in distribution. So this would be something like convergence in distribution, and you have basically separate, but you don't have to know this, and I can't possibly explain this as well. But again, now what we have here is this thing. So because I'm assuming that by the law of large numbers, in limits, I know my v upon n will tend to expectation of vi. So this is n upon v. So you will of course have 1 upon expectation of vi here. So once you got this, you know that your expectation of this thing is just this thing. And because expectation of this guy is 0, expectation of this guy is also going to be 0. So now what you can conclude is, because expectation of mu, let me just say, so again, you can take expectation because this is sort of acting as an estimate, right? This is not some estimate. So minus mu is equal to 0. This implies that expectation of mu hat is just equal to mu. Maybe I should just start off with this, which is just equal to mu, because this is the population, right? So this is just one particular statistic that you have. So yeah, this is the population statistic, and this is the sample estimator. So it's just going to be equal to mu. And this kind of makes sense because in expectation, the transition rate that you derive from the sample, in expectation, it should ideally be equal to the population mu, right? And okay, that does make sense. Oh, they haven't done that up until now. All right, but you guys know, right? So now they have also went further to derive the variance of this particular guy. So again, variance of everything here. And because you kind of know the variance of this numerator, what they've done is they've just taken this n square and expectation of vi, which are constants, as outside and squared them, and variance of this d minus mu v, which is just the expectation of d, as we have seen earlier. So once we have that, then you will just basically you can expand this expectation of vi. So what you will get is, again, what was my expectation of vi? It was v upon n, right? So this is just v1 plus v2 up until v capital N. So if you take this square, this is square, this square, this also becomes square upon n square is equal to expectation of vi square. So now you see, instead of expectation of vi square, you only have this whole term. You are just adding all of these and you square them. And again, because they are using the fact that all of these expectations, all of these, I guess they're just saying that, in expectation, these V1, V2, and Vn are all the same. Then what you will have is just expectation of V the whole square here. So I guess this should be pretty clear. Does this make sense to you guys? And that is how you will know that, your mu tilde minus mu follows normal distribution with mean 0. So again, how does this guy get its normal distribution? Just because this guy has normal distribution, and this is just acting as a constant, right? So because this guy has normal distribution, this guy also has normal distribution, but with some okay, so now because we aren't specifically talking about mu tilde, it's mu tilde minus mu. So that is why you see expectation as 0 and the variance as what we have just derived. So now once we have that, what they are trying to say is that, we also know that that expectation of this guy is 0. So I know that my expectation of d, which is in the numerator, is, can be written as mu times expectation of v as well. So if you rewrite that and substitute it here, expectation of v and this square will get cancelled. And what you will be left with is mu upon expectation of v. So that will be your variance of mu tilde here. So again, why is the variance of mu tilde that? So if my variance of mu tilde minus mu is expectation of d upon expectation of v square, which I can rewrite as mu upon expectation of v, I know that I can rewrite this as variance of mu tilde minus variance of mu, but I know that this is just my population statistic. So the variance of this guy is going to be 0 always. And that is why if you have a look here, what you will see is your mu tilde has normal distribution with the mean mu, as I said, and the variance precisely the same as this guy would have, because the variance of mu is nothing, it's just a constant. So by subtracting mu from each observation, you won't necessarily change the variance of the stuff that you're looking at. Does this make sense? So this was all done basically, just to derive this particular thing, that my mu tilde follows normal distribution with mean mu and variance mu upon expectation of V. So you can see, the variance of this mu, the variance of your transition rate depends on one, its actual value, and two, it's the expected number of time you will be observed. So I think it kind of makes even much. I mean, ideally it would just be, expectation of D upon expectation of V squared, which again makes intuitive sense. But again, now that you have mu upon expectation of V, that's also fine. It's just saying that, your variance will differ by the times you expect to be observed. So I guess that is the thing that you need to know about the asymptotic distribution of mu tilde. So again, we call it asymptotic because it is based on one central limit theorem and two law of large numbers, which all assume that your n is tending to infinity. And that is why you have asymptotic. So this is what you expect your distribution of the transition rate to be whenever you observe large number of lives. So again, that how large. So if 8 is too large, you never know. But again, that is the best you can do, at least once you know this. So I guess this is all you need to know about the distribution of mu tilde. Any doubts so far? Anyone? Okay. So I'm taking that as a no. And let's just move forward. So I guess this is pretty interesting. Let's try to solve this particular question. So who would want to read this question? Savri, can you read this question for us?
Yes, ma'am. A scientist identifies 1,282 newborn wild beasts and observes them during their first year of life on the savanna. The scientist wishes to calculate the constant transition intensity over this period, covering all types of death, including natural causes, and ending up as a tasty snack for passing carnivores. If the true transition intensity is 0.18, calculate the probability that the scientist observes a mortality rate in excess of 0.2.
Okay, so forget about this. Okay, let's just try to decode this first question, okay? I see first sentence, a scientist identifies these many newborns. So from what I know is that my n is going to be equal to 1282, right? And observes them during their first year of life. Okay, so maybe they haven't given this in terms of number, but I know that the observation period is 1 year. Okay, this is my total observation period for each life. And now on Savannah, whatever that is, I think it's some festival or something like this. But yeah, the scientist wishes to calculate constant transition intensity, blah, blah, blah. Fine. If the true transition intensity is 0.18, so they are saying that your true transition intensity, which is just mu, is 0.18. What is the probability that the scientist observes a mortality rate in excess of 0.2? So you want to figure out the probability that your mu will exceed 0.2 at one particular time. So first of all, just by looking at this particular thing, so again, this should ideally be estimator, because again, I know my mu for sure. So the probability that it will exceed 0.2 is 0, because I know my mu is 0.18. So you have to remember the estimator tilde here. So once you have this, again, I want to know what all do you think you should know if you want to figure out this probability. What else should we know?
Distribution of mu.
Exactly right. So we should know the distribution of mu. So we don't have to derive this again. So we can easily assume that it's normal and its expectation is mu, which is given to us. So good, 0.18. But to figure out its variance, what do we need? We need mu and expectation of v, right? So we'll have to calculate expectation of v now. And how can we do that? Any ideas? How can I figure out expectation of V? So think of all the connections that we have of V and think of what V represents. Sorry about that. Must have been terrible for your ears if you're using earphones. Any ideas so far on how should I go about calculating expectation of V?
We can use a relationship between expectation of D and expectation of V.
Okay, that's good. And what is that relation? I think it was something like expectation of D is equal to mu time expectation of V, right?
Yes, ma'am.
So to figure out this mu will just go in the denominator. Okay, but for that again, we'll need to figure out expectation of D now. So how do you think I should go about figuring out expectation of D? So remember, what is my expectation of D? It is just the probability that my DI will be 1, right?
Yeah, so we know the survival probability, that is e raised to minus mu t. So we can calculate it by 1 minus e raised to minus mu.
Exactly, right? We can figure that out. That's good. So let us try to kind of use what Mihir is trying to say is. Okay, so what we want to do is we want to figure out expectation of D. Okay, and what I know is the probability that my DI will be 1 is what? It is 1 minus e raised to minus mu, which is what? 0.18 times t. And what is my t? T is just 1, right? So 0, 1, 1 minus 0, 1. So t is just going to be 1. So this is the expectation that a particular life will be dead. But again, how many lives are we observing? We're observing 1 to 82 newborn wild beasts. So what you want to do is to figure out the expectation of capital D, which is nothing but expectation of D1 plus D2 and so on and so forth till D1282, right? And I know that all of these DIs are just equal to each other. So this will be 1282 times 1 minus e raised to minus 0.18. Does everyone agree with this? Okay, good. So now once we have this, we can easily figure out our expectation of V, right? So let me just erase all of this drawing. And now what we can see here, this is precisely what even they have done. Yeah, at the end they get the same thing, right? So they write it in terms of, so again, if you write Q0, what does it mean? So again, if you write Q0 and if you don't write anything here, it kind of means that it is 1. So it is assumed that you're observing this particular life over one time period. So that's given. And this is how you figure out expectation of D. And you can figure out this, you will get expectation of V. But this is just one method. Or you can also use the actual derivation of, the expectation of DI, where you take into consideration of the probability that this guy will die. Basically the same thing that we have done previously. So here BI minus AI is what? Just 1. That is why you have e raised to minus 0.18 times 1. And you will get the same answer. Oops, no. This is expectation of VI again. So remember, to figure out expectation of V, you will have to multiply this. And then you get this answer. So this can be a bit tricky. But again, I would say, even this could have been trickier. So if you might have forgotten to multiply this 1 to 8 too. So always remember what variables we are working with. So I guess that's good. And once we know expectation of VI, I know this mu, I know this variance. So all that I need to do now is just substitute in this, and I'm just figuring out the probability that this mu's estimator is taking a value which is higher than 0.2. So I write this standard normal and 0.2 minus its mean upon its variance. So I guess that is, upon its standard deviation, of course. So once you have that, you can figure out this stuff, and I guess that's really not new to you guys. So again, this is exactly the probability that you have to figure out. So these are the kind of sums actually that you will be having in the exams, and you won't have to sit and derive this distribution that we just saw the derivation of. So I guess that's a bit nice. That's something nice. Okay, so next up, what they are saying is that most of the times you won't have to actually use each of this stuff. So there is another method to figure out the distribution of mu, which will again give you kind of the same answer. Not exactly the same answer, but it will give you kind of the same answer. So have you guys heard of Kramer-Rao lower bound? I suppose it was there in CS1, but it wasn't specifically used a lot, I would say. So again, what I'm going to do now is discuss an alternative method of obtaining the distribution. So again, I think it isn't again relevant on how you arrive at this. So if you have a look at page number 23 in your table booklets, you will see a formula for Kramer-Rao lower bound, which is just, -1. So it kind of says, so can you all see, or maybe, I can actually do this. So you guys can take a screenshot, okay? What I'm gonna do is maybe start my video, allow. This will be back camera. I guess, yeah. So now can you guys, wait, I can't see myself. Yeah, so if you guys don't have the thing, do this, I guess. Yeah, so now what you have here is, can you guys see clearly?
Yes, ma'am.
Can someone read what the asymptotic distribution paragraph says? Okay, maybe I'll just do that. Okay, it's easier for me. So I'm just gonna stop videos. Yeah. So what I'm gonna do now, so it kind of says that so I'm going to convert it all to mu. If mu hat is the maximum likelihood estimator of a parameter mu based on a sample, then mu hat is asymptotically normally distributed with mean mu and variance equal to the Kramer-Rao lower bound. And again, that is the result that there is. You don't necessarily have to get in the proof of it. So that's good, right? And what is the formula for Kramer-Rao lower bound? It's this. So forget about this CRLB name. What you care about is the variance of this thing is given by this formula. So this is what your table booklet states. And again, this is just d square log L upon d mu square, which we saw is just minus d upon mu square. So if you figure this thing out, you get your variance of this guy as this. So if you have a look, what is your expectation of d? It can be written as mu times expectation of v, right? So if you see, everything will get cancelled out and you will be left with expectation of v at the end. But again, now let's see, and it clearly says you won't have to derive what is your expectation of this estimator. The theorem actually says that this expectation is equal to its population value. So this is good, I guess, for us. So now if you were to figure out its distribution, this is precisely what it says. And again, they are using this particular fact to now do again some simplification for this particular result. So let us try to have a look at that. This is kind of important, I would say. So now you know that your variance, of mu tilde is what? It is something like mu square upon expectation of d. But again, this is in terms of, the population parameters. So what we are going to do is we will replace mu by mu hat, which is its estimated value, and we are going to replace expectation of d by d. So the expected number of deaths that you observed will be equal to the actual number of deaths that you observed in the sample. So this is not the actual number of deaths you observe in the population, but the actual number of deaths you observe in the sample, which we consider is representative of the population, and not any representative, but a very, truthful representative of the population. So once you consider that, what you get here is mu hat square upon d, and then you just multiply and divide by d here. So no, sorry. Yeah, so what you have done is you have mu hat upon d, and you'll be left with another mu hat here, right? So what you kind of do is using that expectation of d is equal to mu times expectation of v, you rewrite this mu hat as something like in terms of these d and v. So again, this will be multiplied by d upon v. So this d and d will cancel each other out, and you will have mu hat upon v at the end. So I guess that's clear, and that will be your variance of mu hat. So previously what you had was mu upon expectation of v, right? So this is not much different, but yeah, something similar to it. So again, they've just written in bold that sometimes the denominator v is also known as, central exposed to risk. And why central? Because it is the central expectation, and exposed to risk is again the time, it kind of says the time when a particular life was exposed to risk. So here we are talking about all the lives together. So V is the total number of time each of these lives together were exposed to risk. And because it ideally, small v here is representative of the expectation, we have this as central exposed to risk, and this is denoted by EXC. So I guess that is about the alternative way of figuring out basically the same kind of distribution for your mu, which is the transition rate. So this whole chapter is about mu. And once we know mu, I know it's easier for us to figure out the transition probability, which is what is another concern for us. So now what we are doing is, again, once you have this mu, you can kind of assume different models. So the only model in this chapter that we are going to have a look at is Poisson model. So we are going to consider again, and so we'll be studying another which is binomial model as well for the same thing. And what we're going to do now is just concern ourselves with using the Posva model. So again, not to remind you guys, but we've already done this a lot of times. So we know that if I'm looking at the Posva distribution, its PDF looks something like this. And I have my expectation as lambda and my variance as well as lambda. So now, for now, I'm going to assume that the number of times that the number of deaths I observe is kind of following Poisson distribution, and that is an assumption. I can also assume that it follows binomial distribution or some other distribution. So for now, if I assume that it is following Poisson distribution, then I get my Poisson model of mortality. So this is again nothing very new, but just another move forward. So what we are going to do is, again, we are assuming that n are the individuals, n is the total number of individuals that you observe. But again, now if we're assuming that there is a Poisson model, okay, so I know that my distribution is given by something like this. So I need to know the rate, right? This is the rate at which a particular event occurs. So what I want to know now is the rate at which death happens. So to know the rate at which death happens, what will I have to do? What do you guys think? How can I figure out the rate at which death happens in the model that we're looking at? Anyone? So what is the expected rate at which you expect your deaths to arrive? So just to break the ice, I would say I am kind of looking at something like this, expectation of D, right? And I know it is what? It is mu times expectation of B, right? So what I denoted earlier, expectation of B, I used, so I can use mu hat for this guy, which will be the population, and I can use V for this guy, right? So what you will have is, for representing V, you used this central exposed to risk. So again, this is just some notation, but ideally what it is expectation of D. So as you know, that if I'm saying that my X is D here, I know that my expectation of D is lambda and my variance of D is also lambda. So what I'm kind of saying is that the number of deaths that I expect to happen follow Poisson distribution, and the rate at which these deaths occur is mu times the number of the times basically they were exposed to risk. So this will be like, let's say if you are if you're observed for 1 year and let's say you don't die, it would be something like 1 year times the probability that you will die. So again, this would be different. This would differ again if you observe like for the whole period. But again, that would just be only one consideration in the total expectation of days that you will have. So this will differ for other people. So this is just like multiplying the time you have observed a particular life, and then this is just multiplying it by the rate at which this particular life will go to the death state. So now that we know that lambda is this, you can easily rewrite the model for your D, which is the number of deaths, as this. So again, that is all that you need to know. And again, we're assuming that these lives are independent and identical. So I guess that's it. And now, if you have a look at this example, here, can you read this question for us?
Yes, ma'am. A large computer company always maintains a workforce of exactly 5,000 young workers, immediately replacing any worker who leaves. Use the Poisson model to calculate the probability that there will be fewer than 3 deaths during any 6-month period, assuming that all workers experience a constant force of mortality 0.0008 per annum.
Okay, right. So, okay, now I am not going to write what this question said to me, and I want you all to decode the question for me and tell me what should I be writing. So, from the first line, what should I write?
Capital N is 5,000.
Exactly right. Capital N is 5,000. Okay. What can I write next?
Observation period is 6 months. Yeah.
Exactly. This is very important, right? So my observation period is 6 months. Okay. What else?
We have to calculate probability of D less than 3.
Good.
And mu is equal to 0.008.
Anything else? Would someone want to add anything to what we have written on the board from the question? So I want you guys to read the second paragraph once again. Mihir, can you read the second paragraph once again for all of us?
Yes, ma'am. Using the Poisson model to calculate the probability that there will be fewer than 3 deaths during any 6-month period, assuming that all workers experience a constant force of mortality of 0.008 per annum.
Okay, and what is my observation period?
Per annum, and our observation month is 6 months, so we need to convert.
Yeah, right. So we have observed my force of mortality as per annum, but my observation period, as Savri said, is 6 months, right? So we'll have to convert this mortality from per annum to 6 months. So what can we do? How do you guys think I can convert this mortality to 6 months from per annum? What can I do? So I want to figure out my mu for 6 months.
And can we convert the observation period in terms of year, like half a year?
Yeah, that is what we'll have to do.
So mu will be mu by 2, right? Divided by 2.
Yeah, exactly right. So it will just be 0.008, and because we have 6 months that we're looking at, and each year has 12 months, so we'll get this particular thing divided by half, which is just 0.0004. Okay, that's good. But now we want to figure out this probability that my D is less than 3. So I know that because I'm looking at pause 1, this is just the probability that my D is 0 plus the probability that my D is 1 plus the probability that my D is 2, right? That's it. So to figure out these probabilities, I want to know my lambda as well. So how do you guys think I should go on to calculate my lambda here, which is the expected rate of death? So it was something like mu times expectation of, central exposed to risk, right? So what do you guys think will happen in this case?
the expected value of death should ideally be number of people into like number of workers into the mortality rate.
Yes, right. So again, what happens here, this question is actually, very good. And the way we did this and the way we started off this question is a bit different than how it's been done in the book. But I guess it's fine. So whenever they say that, we are taking this mu times this central exposed to risk, what they mean is if you must have looked here, they defined this in terms of person years, right? For a total of these many person years. So again, whenever I'm talking about these years, it means, it kind of takes into account, yeah, so it kind of takes into account this as well. So what ideally you should be doing is, if you want to use this formula, what you will have is mu as it is times this. So this will be person years, right? So these are the people that you observe, and this is the time period that you are keeping them under observation. Out of, the conversion rate is being taken into consideration by this guy here. So this is what you will have. But again, if you forget about this formula and if you don't want to remember this, it's fine. All you can do is to figure out the expected number of deaths. You just have figured out mu now. So what you'll have to do is just multiply the number of people that there are with this mu here. So you will get the same answer because we have already done this and only this n is left to be multiplied. And once we have that, I guess it's pretty clear of how you will go to figure out these, because you will just have to substitute this in the PDF of Kurzweil distribution. Any doubts? So again, there's so again, what you can do is you can derive the estimator that we have just tried to use for POSWA as well. So what we will do is, you'll see that this will be the likelihood, right? So maybe I should go back and show you guys this thing. Okay, so keep this in mind. What we have is this probability. And if I use log of L here, okay, so this is again, for one. This is for one particular person here. But what we want to do is, we want to do the same thing for people as well. So now what we are going to do is, we are going to, okay, no, this is not for one person. This is for everyone, right? Because we're taking D, the total number of deaths. This is not DI. So this is for total number of people. But what we want to do is, we want to figure out the estimate for mu again, considering that now we are saying that my number of deaths follow Kurzweil distribution. So, okay, let's just try to do that. So you can again, this is exactly the same equation that you had previously. I guess it is the same. Let me just check once. Yeah, it is exactly the same. So this is the likelihood function that you have. So again, you will use MLE. So you apply logarithm on both the sides, and what you get is D times log of mu plus log of central exposed to risk. And you will be subtracting this because log of this E guy will render the power as it is. And because this is in the denominator, this will go as minus log of D factorial. So now what you will have to do is just differentiate this guy with respect to mu. And again, D of log mu will give you D upon mu. And this will give you nothing, right? Basically 0. So here you will get minus this EXC, and here again 0. So if you do equate this to 0, this should ideally be mu hat, I would say. So your mu hat is equal to D upon central exposed to risk, right? And again, you can check whether it's maximum or not. So I guess you see that you will have the estimator. So again, 5 minutes. So what's happening is, here what you have is small mu, and here what you have is the estimate, and that is why you have a small d here. And here what you have is the estimator, and that is why you get a capital D here. So these small differences do matter. And again, I would say here you should have, so here they have written correctly, but I guess here as well it should be mu hat. So this is again, the way you derive the MLE estimator for mu, using and considering the fact that your D follows Poisson distribution. Okay, so now that we have that, you can just say that, expectation of mu tilde is mu, and variance of mu tilde is again just mu upon this thing. So, there is nothing new in this. Any doubts so far? So I think we should at least see how this were derived. So again, they have actually derived this here. So to figure out expectation of mu, you can actually, so this was the estimator that we derived, right, for mu tilde. And you will have expectation of D in the numerator, and here this is just a constant. And expectation of D, as you know, is just this, right, which is my substitute for lambda in this case. So this and this will cancel each other out, and you'll be left with just a mu here. So I guess that's clear. And then if you're looking at variance of mu tilde, you will again just be looking at variance of this guy. So this being a constant comes out with a square as expected, and you'll have variance of D here. And again, because we know the variance of D is also just lambda here, because my D is Poisson distribution. My D follows Poisson distribution, right? So the number of deaths I expect the rate of deaths to be, distributed with these parameter. So my variance is also this, which is precisely my lambda. And again, this and this will cancel each other out, and you will be left with this guy. So you get what your value for mean and the variance is in this particular formula here. And that is what will be. So again, you can use the asymptotic distribution result of MLE and say that your mu tilde follows normal distribution with mean mu and variance mu upon this sample exposed to risk. So you see now, so all of these three different derivations that we saw, each of these give you the same answer. It's just a bit different with the notations that you use, I would say. So I guess that's it. And again, now the next thing that we have is again just some question again, I would say. So yeah, actually here they're saying that since MLE estimators are asymptotically normally distributed, this is not always true, but I guess we don't care about the cases where this is not true. So yeah, I guess that's fine. Now let us try to do this particular question. Vanshita, can you read this question for us?
Yeah. In a mortality investigation covering a 5-year period where the force of mortality can be assumed to be constant, there were 46 deaths and the population remained approximately constant at 7,500. Calculate an approximate 95% confidence interval for the force of mortality.
Okay, so again, I'm not gonna say anything. Can you guys guide me to the answer? Not precisely the answer directly, but yeah, let's just first decode the question. Okay, so what should I be writing here? What all information do we know?
The time period is 5 years.
Yeah, it is 5 years. Yes.
Number
what else?
Number of deaths.
So my D is 46.
N is 7,500.
Yes. Anything else? So what can I do next? What do I have to figure out? I have to figure out a confidence interval for the force of mortality. So again, force of mortality is just another term for mu guy here. Okay, so yeah, that's just mu. So you want to figure out the confidence interval for mu. But we don't know mu, right? So what can we do now?
Mu will be d upon n, right?
Mu will be d upon
N.
d upon n. Why do you think it will be d upon n?
Because n is the population, so number of deaths upon total population.
Ah, I see, I see. Okay, so you mean it should just be the number of deaths that you have observed upon the total population. So, okay, let me just tell you that let's say if I observe 46 deaths and among 1,000 people, okay, I keep the numbers a bit changed. So let's say I'm saying that I have observed 50 deaths in 1,000 people. And the first scenario is where I observe 50 deaths over 1,000 people in 1 year. And the second scenario is where I observe death of again 50 and out of 1,000, but over 20 years. So where do you think the force of mortality would be higher or lower, or do you think will it be equal in both the cases? So my D and my N is same, right? D is 50 and N is 1,000. I couldn't hear any of you well.
It would be higher in the first case.
Exactly right. It will be higher in the first case because in less period of time, you're observing many more deaths than compared to the other scenario where you have so much time and you have only observed 50 deaths, right? So the mortality is you kind of get the intuition that people are dying at a much higher rate in the first scenario. So you can say clearly that my mu cannot only depend on D and N because in these two scenarios, my D and my NN was the same. So, but my mortality was higher for the first case than the other case. So now what you expect is that the number of time when I'm observing these people, if that is higher, the mortality will be lower, right? So that is why it makes sense to have this to have this V actually. I will write, not exactly V, but let me just erase all of these. And what I can write instead is just EXC. And this would take into consideration not only the N, but also the number of years that we are looking over. So now you have in a way figured out the D that you know already, but you don't know this EXC. So I think let me just erase that, and I guess we have arrived at the answer. And the only part which is tricky in this particular question, which is to figure out the value of mu hat. So once you know this was what you told, but again, you have to take into consideration the number of years that you are looking at. So you again divide it by 5 to get this mortality per annum, right? So now that you have this mortality per annum, what you can say is you are now trying to figure out this confidence interval 95% for mu. And this would just ideally be this thing, right? So this is again 95% value, 1.96 for the standard normal distribution. You can get it from the table booklet. And I guess, let me just show the page number for people who might still be confused with this. So you can actually go, this is like the two-way probability. So be aware of that, and you can have a look at the table which is on the page number 160 and 161. So you'll get somewhere here the value. Let me just, oh no, that's not what we are considering. It will be on page number 162. Okay. So on page number 162, you will get your answer. So this will be basically the 9, because we're looking at 95% confidence interval. Half you expect to go from right and half, let's say, you expect to go from the left. So you'll have 2.5. So for the 2.5 case, you'll see that the value is just, for the 2.5%, on the one side, the value is just 1.96, right? So I guess that is all that matters. And what you'll have here is 1.96 square root of variance of mu tilde, which is your estimator. So again, you know, mu hat is what you have derived here, the value, and this variance will be what you already know the formula of, which is what you got the variance formula from here, right? So I guess that's good. And what you will have to do is just substitute these values now, and you will get your confidence interval. So any doubts up until now? So again, remember the example that we just saw. What we saw was, we knew some information about D. We knew some information about, these lives being exposed, and how much time they spent under observation, and also how many number of people were there. So once we know all of that, we can actually figure out the value of our mu. I mean, not the actual value, but an estimate. Yes, we can certainly do that. So we used the results that we have derived up until now, then to figure out its variance and its expectation, and then we get to a confidence interval. So now what this will see is that out of 100 times, 95% of the times, you will observe the mortality rate in between this particular interval. So many of the times, people kind of say that 95% probability that you'll observe mu in this. So that's kind of not actually true. And because of this very reason, that its actual interpretation is the fact that if you conduct this experiment 100 times, 95% of the times you will see mu in between these numbers. But what happens in actuality is we conduct experiment only once, right? So there is no way you can say that the mu that you have observed is out of those 95% times where you will observe in between this, or out of those 5% times where you still expect from this model that your mu will not lie between these intervals. So again, we know that the very fact that we reject and we can only reject the hypothesis. So the very fact that we reject hypothesis is based on the confidence intervals that we derive, right? So I think, I was exposed to this misunderstanding of p-value, and when I was exposed, it was kind of heartbreaking for me, because every paper that I read and everything that I studied in statistics, I was just suddenly, doubtful of everything that I was studying, because I also saw one article which was about the ban of p-values. So it was a journal of, I guess, applied sociology or psychology or something like that. And they actually went so far as to ban the use of p-values in their journals. So I guess the paper that were published in those journals, but I guess now it's allowed. And there are various other alternatives to p-values that people have tried to come up with. But again, it's not that robust as p-value. So we know that every result that we study, everything hinges upon the existence and the interpretation of p-value that we try to learn. But yeah, I guess it kind of just helps us to know the limitations of what we are studying, so as to be able to, appreciate, I guess, maybe not appreciate if you know the limitation, but again, you would know that again, there is something that there needs to be done. And these theories, there is so much difference between theory and practicality for a reason. So this would matter if you're looking at from a theoretical point of view. But again, if you're someone who is more of a applied and who's more of, in the practical side, you will ignore the chance. And that is what happened that is what kind of happened when we studied extreme value theory. So again, the extremes, the consequences may not be that dire every single time, but there will be some consequences, and sometimes you can live with them, sometimes you can't. So I guess that's fine. But I would say that's all from my side for today, and that is the end of this particular chapter, number 3. And thank you very much, you guys, actually, for staying through for this long sessions, I would say. But yeah, I guess it wasn't that boring, and you guys had some fun at least. Yeah, any doubts? Vanshita, did you try to say something? Because I couldn't hear you.
I just said no.
Oh, okay, yeah, all right. So I would just, I guess that's all from my side for today. Maybe I'll just update, in the Google Classroom about our next practice session. And in that chapter, I will not be teaching. So that's kind of good, because this is the basic that we will be moving forward with. So I want you guys to be thorough with these before we move forward.